Okay, thanks for coming to our talk. We're going to talk a little bit about what our team does, the problem we're trying to solve, and why Truffle and Graal are interesting to us. And then we're going to show some actual code of some of the things we've done with Truffle and Graal and some of the lessons that we learned along the way. Okay, so a bit about us. I'm Jackie Haynes. I'm a managing director and tech fellow at Goldman Sachs, and I'm also on the JCP executive committee as our representative, and that's my Twitter handle. And this is Zach.
Hello, Zach Fernandez. I work with Jackie on the SecDB team.
So our team at Goldman Sachs is called SecDB Architecture, and that stands for Securities Database. And we're part of a core engineering group which sort of sits across Goldman, so we develop the core technologies that are used in all the different parts of Goldman Sachs. And our particular system that we look after is responsible for supporting and evolving an in-house programming language that we've had for 25 years, and it's used for some really critical applications. It's used for all our pricing and risk and trade booking. And so that's what we do. Okay, so I'm going to set the scene, sort of why we've got our own in-house programming language. So who's seen Wayne's World? Hey. So that came out in 1992. So transport yourself back to then, get in that mindset. And that's sort of roughly 25 years ago now. And so it's 1992, and at Goldman Sachs we're working in foreign exchange, and we want to code in a dynamic language. So we've got clients on the phone, we want to prototype deals pretty quickly, and we've got quite a small team, so we want to start sharing code across the different asset classes. So in 1992, Python doesn't exist yet. It's just starting out. The 1.0 release was in 1994. Ruby doesn't exist either. It's 1996. Java, it's not a scripting language, but it's also not there yet. So what do we do? Or what did they do? I wasn't there. So there is Perl. 1987. And I have to say I'm pretty glad they didn't choose to write the system in Perl now. There is Visual Basic, that was there 1991, and it's a great programming language to learn. It's not super sophisticated, not a huge, not as complex, or doesn't have all the features we might like. So obviously the solution is we should totally write our own programming language. And so that's what they decided. That the person in the tie there is like the business people with the money going, are you sure you should be doing this? But they kind of already had. So this is the scene back in 1992. And so that was the birth of Slang. That's what our language is called. It stands for Securities Language, but I think they enjoyed the pun as well. It is interpreted, it is single-threaded, and syntactically it's the love child of C and Lisp, but with spaces in variable names, because we wanted it readable. And that was kind of what was around in 1992, so that sort of explains some of the influences. And for those of you sort of wondering a bit more about it, so you can think of it a bit like Python today. So there is a dynamic scripting language with C and C++ underneath that are kind of doing all the heavy lifting. And so this is Hello World in Slang. So it looks kind of normal other than the spaces and variable names. And so it's not just Python. They built a number of features that are pretty unique that help with pricing and risk. So one of the things about computing risk is you have all these inputs for your price, and you want to modify those and see the results. So you kind of shock the inputs and say, what would happen if this happened? And so it has an inbuilt kind of graph. So you can think of that a bit like a spreadsheet. It's inspired by a spreadsheet, and it memoizes the values. So there's quite a bit of memoization going on, and then you can diddle or change the values and see your risk. It also, even then, right, it was super important to have data and code kind of integrated. So they had we also have an object DB that we built all the way back then with global replication to Asia and London, because we were trading globally. And so that's pretty unique, and it's very built into the environment. So the code is stored in that database, and all the pricing and risk data is there, and there's a lot of features that you would recognize from data science environments today, where there's a lot of things to show data and get nice graphs and tables out of it. So it's an integrated IDE, and it's also a rapid development environment. They wanted to be able to make changes really, really quickly. So code can be pushed globally in a minute. So if you find something's wrong, you want to kind of correct your algorithms and things pretty quick, and that's pretty cool. But the thing that really caught on is it was pluggable. So everything is an add-in in our language, even for and if. And it's pretty easy to extend. And so it really took off, and it's still used today, even though it's 25 years old. And all the teams collaborated on that. So it was like a open source mono repo before we knew what those were. I shouldn't say open source, an internal collaboration environment. And so, bringing you back to the present, it's 25 years later, and we have 150 million lines of Slang, and it's still very much actively used and running our pricing and risk. So it's a big thing. It was super successful, and so the eagle-eyed of you might see this little dip here, which is when we rolled out some auto-deletion code to start deleting things that aren't used, but it's not making a huge dent, as you can see. Just to put this in context, right, the Linux kernel is roughly 25 million lines, Windows 50 million lines, so 150 million is quite a lot of code. And that means as we think about evolving this, it's not as easy as saying, oh, let's just rewrite in Python tomorrow, right? That would take a long time. And underneath it's C, C++, so we've also got about 10 million lines of that for all the add-ins and the optimized quant functions that we have. And so it's a really cool language, but it has some challenges that our group has to wrestle with. So there's no language specification. This is definitely something that kind of grew over time. It was definitely very much a time-to-market thing, and oh, we like that cool feature, we'll just add that. And so it's got several type systems, and they're all still in use, which is great. It's got several types of error exception handling, as they started to see different languages over the years have better mechanisms for that and bring them into the language, but no one wanted to go back and retrofit all the older things. And it's got several approaches to memory management in the C++, so we've got some copy on write and some reference counting. And so it's a challenge for us. Like we want to continue to optimize it and sort of think of a path, perhaps off of it, or over the longer term, or perhaps not. Perhaps just to bring it up to kind of modern standards of language. But it's very hard to optimize. It's a complex C and C++ code base. There have been previous attempts to optimize, so we have compiled Slang and mini Slang, so they've tried to create a kind of bitcode or LLVM sort of versions, and those we're successful in kind of a narrow way, right? It's very hard to support all the parts of the language. So those have really not made a material impact and are used in very specific places. Yeah, and then, as I mentioned, it's, we've got a lot of it, and we're actively supporting it. It's currently live. So as we think about solutions for evolution, it's definitely an evolution story. We're looking at ways to evolve it rather than like revolution, tear it down, start again. So that's our problem space. And just a little bit more of our goals as our team thinking about owning this language. So we definitely want to have more of a path to interoperate with and or migrate to other languages. So we have interop with Java over JNI, but you're all aware that has an overhead. There is interest in potential interop with R and Python because people want to take advantage of the libraries that are available in those spaces now. And we always want to improve the speed of execution and reduce the cost of compute. We have to run market risk and credit risk every day, as well as all the different regulatory risk scenarios, and that adds up to many, many hours on your compute farm. So there's actually some huge benefits we can have if we can shave off a few percent or make our language significantly faster. And we're thinking about the future, we can sit down and look at all the kind of techniques that people have applied over the years to optimize Python or other dynamic languages, and we can start to sort of apply them also to our language. But wouldn't it be nice if we could take advantage of the work that's already out there and what other people have done to optimize, rather than owning our own very complicated interpreter, because it's kind of a nice, simple AST interpreter now, so from a supportability, sort of working on the code base, that's nicer. And the more optimizations you put in, sort of the more specializations you get, the more complex it is to maintain. So it would be really nice if we could run on perhaps someone else's VM or some other stack and get the advantages of the participating in that community and the performance improvements that other people have already come across. And kind of the last part is it's kind of got even more important these days as developers move around different companies. They're used to quite a high standard of tooling. So it'd be nice not to have to write all the tooling ourselves, right? Which we do have a debugger, we do have an IDE, but wouldn't it be nice to get some of that for free and to plug into all the things that exist? And we also, these days, C++ is a hard language to do well, and so hiring C++ developers, especially sort of who are also going to be good at working on an interpreter, that's quite a niche. So we're also interested in sort of the longer term having something that's kind of easier for our team to work on. Okay, so why Truffle and Graal? How many people know what Truffle and Graal are? Okay, good, great. So a quick recap. So Truffle is a Java library that helps you write an AST interpreter for any language. So you write it in Java, but it can be used for any language. That goes with Graal VM, which is a universal virtual machine that's designed for a polyglot world. So it's designed to have, with the idea of having interoperability between languages. And I'm just going to mention Seulong as well, because we're going to talk about that a bit in this talk. So Seulong is a high-performance LLVM bitcode interpreter that's built on Graal VM, and that's interesting to us because that means we can also run the C and C++ code if we compile that to LLVM, so we can interoperate. So when you bring all those together, so the promise of Truffle and Graal and Seulong is we get high performance, so you write your Truffle interpreter, and with a sprinkling of some annotations, it does optimizations for you. It comes with a lot of things, and there's some examples out there that you can look at for Ruby and JavaScript, so you can see how to do that. You've got a garbage collector got the VM. And this bit, which sounds pretty magical, is like zero overhead interop with C++ using LLVM. So that would be kind of cool if we could just call it for free. And language agnostic tooling. So it also provides a debugger, a profiler, and a heap viewer, and some APIs so you can add more. That's kind of a growing ecosystem. So that's why it's interesting to us. So we decided it was definitely worth just doing a proof of concept to see, is this is a direction we want to go? And so I'm going to hand over to Zach, who's now going to talk through the details of how we did that and show a little bit of code.
Thank you, Jackie. Hello, everyone. All right, so basically when we sat down and started initially talking about how we wanted to approach this problem, we kind of settled on two approaches. And I know Jackie mentioned earlier that we're looking for more of an evolution than a revolution approach. But being developers faced with an aging code base, of course, how many people here would actually sit down and not consider the Big Bang approach, right? We all want to burn it to the ground and write something new and shiny. But of course, is it practical, right? So it does give us a clean split, but we have to worry about the type system, right? We have about 350 built-in types that we would have to figure out how to rationalize, potentially rewrite in Java or something else. We have a large number of built-in functions, right? We have on the order of tens of thousands of built-in functions. And again, these are, could be pretty standard built-in functions like print. We also have math-optimized add-ins that are used for quants for pricing and risk. So quite a lot of variation there. And the built-in functions today have quite a bit of freedom. So you can actually give them kind of a handle to a node in the parse tree, and then they can rewrite that, manipulate that. So that's also kind of a tricky thing to address. Right? The incremental approach gives us obviously a little bit of a lower barrier to entry. Right? It allows us to potentially take advantage of parts of Truffle Graal, right? Some of the promise of Truffle Graal, which is that you can get some of the tooling, like a better debugger, a better profiler, and then potentially you can bring bits into Truffle and take advantage of things like the just-in-time compiler, partial evaluation, and get the better performance, right? And the idea is that this would also kind of build on top of itself, right? Because once you have the better tooling, you can easily identify hotspots, figure out which would actually benefit from specialization, just-in-time compilation, and bring those over. So, of course, we settled on the incremental approach, right? And the way that we went about doing that was we decided to first start with variables. Right? Variables are pretty important to a programming language, right? So we decided to start with those. We wanted to make sure that those were mastered on the Truffle side, right? So the variables would be stored on the Truffle side of the interpreter, but we wanted to make sure that they were accessible from the existing interpreter. We'll come back to that in a sec. Then we wanted to reuse the existing parser, right? We were going to let the existing Slang parser produce the set of nodes that it thought that it needed to actually, run the script. And then from there, make a second pass over that parse tree and identify the nodes that we could actually rationalize and do something with in Truffle land, and basically lift those up and make those native Truffle nodes. Right? And we basically categorize those into three different groups. The primary candidates are going to be your logical operators, things like plus, minus, less than, greater than, and then language primitives. So Jackie mentioned Slang is pluggable. Everything is a function, returns, things like that. We wanted to actually make them kind of more keywords, make it behave more like a standard language that you might have come across elsewhere. So we wanted to lift those into Truffle. Then secondary, the well-behaved functions. So I mentioned that add-ins today basically get a handle to a node in the parse tree. They can manipulate that. They can do all sorts of crazy stuff. Most of them don't. So there's a lot of good candidates that we could actually bring directly into Truffle. And then, of course, the last bucket is going to be kind of the trickier stuff, the nasty add-ins, which actually do manipulate the AST, and some of the data type operations, right? So, nobody wants to bite off the 350 different data types that we have at the moment. So we're just dispatching all of those to the existing C++ code base. Right? And in theory, this should allow us to migrate over the core of the language while continuing to leverage kind of SecDB's rich ecosystem, right? That 25 years of innovation that we have in that space. Right? So let's take a look at kind of how we've done the variables. So there's a couple things here. So first, you can see the existing interpreter. This is the C++ code base that we've been running with for the past 25 years. We have the LLVM bridge, which is running in Seulong. We have the foreign access interop layer, and we have the new interpreter. So kind of a note on these three things. So Jackie mentioned that we have about 10 million lines of C++ code. So we didn't want to basically start off by trying to figure out if we could compile that whole thing with LLVM to bitcode. The C++ makes a fair amount of assumptions about the state of the runtime, everything being in shared objects, being able to kind of dynamically load them. So basically what we did is we introduced a bridge, which is a small piece of code written in C++ compiled to LLVM bitcode. And then we use that to kind of proxy between the new interpreter in Truffle and the existing interpreter, right? And we do that through Truffle's interop layer, right? So Truffle gives you the promise of zero overhead interop between the language boundary, right? And it does that through a set of things called polyglot APIs, right? So the existing API, if you wanted to write a variable, right, it basically makes a call to a C++ class called put variable. Right? And that class we've rewritten and we've compiled it with LLVM bitcode. Right? And so when you call put variable now, that thing makes the jump. So anything in red is kind of the native unmanaged code. Blue is going to be running inside GraalVM. So anywhere you see the transition from red to blue, that basically means that we are crossing the boundary between native code and then GraalVM code. Right? So this put variable code ends up in the LLVM bridge. And then we use the polyglot APIs to import a truffle object, right? Truffle object is basically how you implement interop, right? So this is an object that can be understood by, basically all the different languages that you can run on GraalVM. There's a standard set of APIs for interacting with these things. So you bring this in using polyglot APIs, and then you put polyglot put member, which sends your object a write message. Right? And then on the Java side, this thing is basically, a Java util hash map for all intents and purposes. So we're just dumping the variables in a map, and then we can return that all the way back to the interpreter. Get variable flow looks very similar. Again, we're using the same truffle object. We're reading it, and then you can use get member to actually read an entry from the map and read it back to the existing interpreter. And now the variables, we haven't actually changed how they're actually kind of managed in memory. They're opaque to the Truffle Slang interpreter for the moment. The C++ interpreter understands them, and for our use case, that's fine at the moment, right? And then going the other way is important, right? We want to be able to call our existing suite of add-in code, right? So similar sequence diagram, except the flow has changed. We have our new interpreter on the left. We have the bridge in the middle again, and then we have the old interpreter on the right-hand side. Colors are the same. Blue is GraalVM, right? Red is the native code. Transition is basically anywhere you're jumping over the boundary, right? So we have a simple eval method exposed on the bridge. And what that does is it basically takes in a node in the Slang parse tree, and it will tell the existing interpreter to evaluate it, right? And then we get that result back. And the rest of it is basically unpacking it, because we have to take the return value from the existing interpreter and turn it into something that we can actually do something useful with on the Truffle side. So there's quite a bit of boilerplate as far as actually allocating a DT value, which is kind of the base of our type system. It's like a Java object, you can think of it as. So we have to allocate some memory. We have to pull that out of the result from the interpreter. We have to make a copy of it, and then we have to free it, right? So this is not managed memory. This is still allocated in the native heap. So you do have to free it, otherwise you have memory leaks. There's no magic there yet. I think there is something in plans, but not yet. Right, so looking at some actual code, right? So here we have a Slang native node. This extends Slang expression node. So Slang expression node is basically the root of all Slang nodes. You can think of this as any node which produces a value. Right? Native node is a specialized implementation that will actually call a legacy Slang evaluation function. Right? You can see some annotations here, and this is basically the Truffle DSL. They'll actually run some code generation here. And what you can see is we have a root node. So this is a node in the existing Slang parse tree, right? And it's opaque to us. We don't really care what it is. We just know that it's a node that we can evaluate. Right? And then we have a couple things that we're holding on to, right? So this cache basically means evaluate it once and hang on to it. So this Slang red is going to be the return value from the interpreter. And then we basically have, again, the methods for allocating a way to hold that thing and pulling it out of the interpreter, right? you'll see here, so we're just basically saying eval.call, and then you give it the arguments. So you'll see eval is a direct call node. That's pretty neat. That's something that Truffle can actually optimize, so this can be inlined. And it's neat because this is actually a C++ function, right? So you can see down here, here's the C++ code. So, if you've ever written C, C++, this should look pretty standard to you, right? It's a function, returns an int, it takes in, again, the node in the parse tree. So you can see we actually have a handle to that. We're just storing it as an object. When it gets passed through, the C++ code sees a pointer, and then the memory that's going to hold the return value, and then we just delegate it to the existing interpreter, right? So fairly magical how it all hangs together. There's no JNI, there's no anything like that, right? You call eval, it calls some C++ code, which is all transparent to you, right? So from here, we basically have the building blocks that we wanted to start with before we could actually go off and start incrementally moving Slang over. So let's define the evaluation criteria that we use for the proof of concept. Right? So here we have some beautiful Slang code, right? Spaces and variables, yep, definitely Slang. So here, it's fairly simple, but it has a couple things that are nice because we were hoping to prove them out as part of the proof of concept, right? Only 15, 20 lines, but you look at it and you see, okay, we have a variable assignment. This is a global variable, right? Slang does have scoping, it's good. There's a local variable here, again, assignment. This is a data type operation, which is opaque to us. There's a for loop, we're writing variables, we're incrementing, we're appending to an array, so that's a data type operation, which again, we want to be opaque for a period of time. We have an add-in function to sum up all the numbers in this array. And then, of course, we have basically the function signature, right? So this is a function which takes in two doubles, left-hand side and a right-hand side, and it returns a double. And then last but not least, we have the invocation. So basically, what is kind of that formalized, right? So first is, can we get Slang to work? It's a super important question. I don't think your manager would be super happy if you went off, noodled on some code with a goal in mind and couldn't even get that first primary goal to work. Then interop with existing data types and built-ins. So again, mentioned this a couple times. There's a huge amount of existing data types and built-ins. Don't want to have to rewrite all of that right off the bat. We want to be able to do that incrementally. Then the tooling, right? Can we get the profiler to work? Can we get the debugger to work? This would be great for our users. This would be a huge win if we could get them better tooling. Of course, performance. So Slang is not fast. So obviously, any improvement in performance would be another awesome big win for us. And then last but not least, is Truffle easy to understand and implement, right? If we decide to go down this route, is this something that we could conceivably support moving forward, right? And not have to hire kind of specialized engineers, but it's Java code. Can we get Java developers to actually maintain this thing, right? So what did we find? So the good. So the tooling basically works as advertised. It was fairly low overhead to actually get the debugger and the profiler working. So we got the Slang POC running. We were able to hook that up with the debugger and the profiler, kind of verify it, see it in action. The node DSL made it easy on whoever was writing, which was me, to implement nodes which handle specialization and invalidation, right? So like I mentioned, Slang has an interesting type system, but of course there are some primitive types like numbers and strings. If you do want to write some code, and we will eventually moving forward, that isn't dispatching messages for, let's say arithmetic between two doubles, you can express that very easily with the node DSL, and Truffle will take care of, if your invariants change and you no longer have two doubles, it will invalidate it and it will kind of respecialize the code and recompile it, things like that. So that's very cool. Again, if you do have interop, so we do between Slang and C++, if that is all running on Graal VM, then you do get kind of the integrated environment. You can profile across those boundaries, you can debug across those boundaries. That's just a huge efficiency win. That was very cool. Of course, Seulong, it did work as promised. There was definitely some bits that kind of blew my mind, a little bit of magic. Writing a class, compiling it to LLVM bitcode, handing that pointer off to our existing interpreter, and then that interpreter being able to call member functions, which would end up kind of in Seulong managed code. That was all very cool. the C and C++, it was performant, it was optimized, that was neat. And then as far as actually implementing this, I found the documentation to be pretty solid. Truffle is well documented, and fortunately there's a lot of quality examples on GitHub, right? We have several implementations already out there. There's Simple Language, which is a nice starter project, and you have a couple more involved ones like Truffle, Ruby, and Seulong, which are kind of useful just to look at and see, what other people have been doing. So burden of proof here. You can see here's kind of the debugger. You can see here's some Slang code. This is an add-in, right? Here's C++ code, so you can see, basically you end up with the call stack. You can switch between them, right? So here's the Slang code, here's the C++ code. You get a handle to a variable. You can actually evaluate it. So this was pretty cool. This is not what our type system will look like long term, but for now, this is actually, the variables are just C++ pointers, and so being able to actually look at that in the Slang debugger, be able to kind of unroll that, see what the pointer looks like on the native side, that's all very cool. Right. But of course, it's not all rainbows and unicorns. That would make for an incredibly boring talk, so there were a couple things that didn't work out for us. And a lot of that, I think, is basically a result of our mixed environment, 25-year-old C++ code base. So we've been a GCC shop basically forever. Seulong currently requires libc++ if you're writing C++ code. Again, because we're GCC, we use lib standard C++. I naively dropped that in, and everything seemed to work fine until it didn't. So the layout of exception data structures is slightly different, which meant that if something went wrong, you basically wouldn't be told about the exception, execution would continue, and then it would crash later when you did something with that chunk of invalid memory. The Seulong debugger was not as mature as something like GDB, which meant that when things went wrong, it was kind of tough to be able to figure out what was going wrong, why it was going wrong. Right? And that interaction also between native code and the virtual machine can be hard to trace. So, when the Seulong debugger didn't kind of give me the data that I needed, I tried to use GDB. What I found was that GDB couldn't give me the full backtrace into the native code that was invoking the LLVM bridge because it doesn't understand the virtual machine frames. So you couldn't actually unwind through the Graal VM stack. So you couldn't see where your code was going wrong. Of course, anybody who's ever used JNI, there was significant overhead when the code needed to actually leave Graal VM and go into kind of native unmanaged code. And so that basically led to performance of current Slang and Truffle is a bit too slow. So I think, things like wherever we're crossing the boundary, it's basically like an order of magnitude slower. And then documentation again, it was good, but there was also some places where it led me astray or I was looking in the wrong place. So, it's a rapidly evolving project. There's obviously a lot of investment going on, a lot of changes going on. So sometimes what I found was that the code and markdown files on GitHub and what was actually on kind of the product page were out of sync or they didn't represent the same information. So a couple times there, I just ended up spending a little extra time trying to track down what I was missing. Right? And so just kind of a quick picture of the Seulong debugger here, show you a little bit. Hopefully you guys can see this. It's a little bit small, I'm sure, but basically here, this is a fairly simple C++ program. So here you have a simple struct that has a char array, it has a double, and it has an opaque pointer, right? And so here we're basically allocating hello world, then we're dynamically allocating a string on the heap, and we're copying that hello world string. We're initializing struct s with, again, some of these strings and a double 10. Again, we have another hello world string. And so what you actually see on the right-hand side is this, the variables. And so the char array, it tells you it's unavailable, so you know it's there, but you don't know what it is. Struct s, similar. You can see what the fields are. You can see the value of the primitive double, but anywhere where there's a pointer, you can't see what it is. And, down here, like in GDB, you can dump kind of characters at a memory location, poke around. With the Seulong debugger, you can't actually evaluate anything interactively yet. So basically, you can see local variables, you can evaluate the stack trace, but you can't get a whole lot of information about what is actually going on, right? Which can make it slightly difficult to debug. Right? But quick shout out to Oracle because we have come to them with several of these problems, and they have been very receptive. So, one API that we actually asked for was polyglot has member, and we basically use that when implementing the variable support. So that's, does a variable exist? So they actually added that for us. It made it into RC7. There's a GitHub commit, again, burden of proof. Exploration of lib standard C++, right? So basically, can we do something about lib standard C++ so that we can use it instead of having to figure out how to make our existing environment work with lib C++? I've heard that that made it into RC8, which came out, I think, yesterday or recently. So I haven't actually played around with that yet, but if it did, that's awesome news. GDB stack unwinder. So for those of you familiar with GDB, this is actually a feature which has been introduced in newer versions of GDB, where you can actually basically add your own stack unwinder and teach it a bit about stack frames. And there has been some discussion on the JDK mailing list from Red Hat folks about implementing one of these for Java. So I'm hopeful that there will be some movement around getting one of these implemented for Graal VM, which would then allow you to unwind through VM frames and kind of see the entire stack, basically where you're going from native to Graal VM back to native, right? Seulong debugger, again, we did discuss basically being able to evaluate expressions interactively. They said that they would take a look at that. I have no idea how easy that is, how hard that is, if it's going to happen, but thank you anyway. And then the Truffle license change from GPL to UPL. We didn't ask for that, but that's just awesome. So UPL is a very permissive license, so thank you for that. All right, so then where do we go from here? Right, so we have a basic proof of concept. We've proven that we can kind of run Slang on this, but like I mentioned, the biggest thing is definitely performance at the moment. So we'd like to explore Substrate VM. So show of hands, how many people have heard of Substrate VM? Okay, so Substrate VM is basically, it's like Graal VM, except ahead of time compiled, right? So, you can compile your code to actually a machine executable, and then run it on that, right? And Substrate VM offers additional options for calling into C. So you can actually say, I don't want the prologue and the epilogue associated with kind of that J and I transition. So slightly less overhead per call, so that seems kind of interesting. I don't know if it will have enough of an impact, but worth exploring. Obviously, the one thing that we think is probably going to have the most impact will be the more code of ours that we can actually bring over and compile with LLVM. Fewer times you have to leave Graal VM, make that cross over the boundary to the native code. You're going to see massive benefits there. But like I mentioned, there's definitely some trickiness there just because of the assumptions that our current code makes and just the size of the code base. So, then of course, to date, we've only done a very small subset of kind of Slang language. So you saw the proof of concept, it's only 15, 20 lines. There's quite a bit more to go. There's definitely some tricks that we can apply, again, as far as specialization, right? So where we have, two primitive doubles, we can do the arithmetic directly in Java. There's no need to actually go to Slang's type system and ask it to add the numbers, right? So, the more that we actually pull directly into Truffle, the more we write into Java, again, we should see some pretty significant benefits. The last thing, which we know exists and is on our radar, but we haven't actually thought too much about what we're going to do moving forward, is that by using the Slang parser to produce the Slang parse tree and then kind of walk over it a second time and convert part of it to native Truffle, in some cases you do end up duplicating memory, because you might have the same object referring to the same node in the parse tree, right? Two different objects referring to the same part of the parse tree. So obviously that could be problematic depending on how many things we leave kind of as a wrapped native node. So that's next on our radar, right? So just to kind of revisit and summarize, right, how we did. Can we get Slang to work? Yes, we can. Can we interop with the existing data types and built-ins? Again, yes, not as fast as we would like, but we can do it. The profiler and the debugger, I was very happy to see that it wasn't a lot of work to get it working. Having played around with some of the existing ones for Slang and seeing kind of how much machinery is involved around making it work sensibly, I was pleasantly surprised by how little effort was actually involved there. Better performance, a bit of a question mark there. And I think we probably can get there, but it's going to require, kind of some rethinking about our approach and figuring out where we can eliminate hops to the native code. And then is Truffle easy to understand and implement? Yes. I mean, I think we've spent probably 6 to 8 weeks doing this with just a single developer. And, we were able to make decent progress, get a decent amount of the language working, get the proof of concept working. I'm not a compiler engineer or anything like that. I'm just your fairly run-of-the-mill Java developer, C++ guy. And so, it was pretty easy to reason about, look at what other people had done, prior art, and just kind of spin it up. So, yeah, definitely promising results there. And I think at this time we're going to just turn over for any questions. So.
Stunned silence.
Yes.
It's a lot.
What would it take for you to fully move to this? What are your next steps? How much investment are you putting into this? What's next?
Okay, I'll just repeat the question. So the question was how much investment would it take, and what steps are we putting in next? So this has been pretty promising so far. So we've taken a checkpoint because we had to give a talk on it. So, but we're definitely encouraged by what we've seen, and so we're going to continue with the POC. I think the big question for us is going to be the performance. We haven't, partly because of the way we've done it, rather than anything very specific to Truffle or Graal, because we're trying to, interact with an existing code base. We need to see that. So I think we're definitely going to take more of the language primitives into Truffle and see what speed-ups we could get. So if we take things like for loops or arithmetic and start specializing that, then that would be pretty cool. I think how much investment would take, I think what would be interesting for us as a decision point is, so if we go a bit further and start to see what kind of performance benefits we can get, if we can show that that's actually pretty promising, then that will sort of drive our, right, we'll just commit and we'll start putting kind of everything into Truffle. There's a few considerations here, right, because we'd also be sort of committing to use Slang and compile our C++ code with LLVM, and we don't know if that's going to have any sort of strange sort of performance or memory issues. But I think the benefits we would get from being able to have a much faster interpreter may weigh that out. But I mean, I don't know, but from what I've heard, so I think there was a period where it went through a lot of rapid investment, fairly early on. And so at that stage, there weren't really any sort of super attractive alternatives. It would still the mixture over a ObjectDB built in with all, extendable kind of, Python wasn't mature yet. There wasn't really an alternative. Now, in the last at least 5, maybe 10 years, we've seen a lot less investment in the core because it's all been running so well. But I think what has meant that it's continued to be so successful, despite it's kind of getting people to work when they have to use a proprietary language. We're hiring people and making them use our language. What has kept that going so long was actually just how easy the whole integrated SDLC is. So you turn up, you write Slang code, you push it, and it's globally in production within minutes. It's just straight, and it's out, in Asia. And so the productivity and all the tooling that has been built into the environment has made it so it's sort of, there's a tension between, oh, we wish we had a language that we could just Google and use someone else's examples versus, oh, but we've now got all these really cool libraries in Slang for like curves and dates and all these things we need, and we can push code really easily. So it's kind of kept going in that sense. But I mean, I think it had got to quite a large side kind of before there would have been that point where you're like, well, hang on, should we just use X? It's also a little bit interesting because I keep mentioning Python, but I think that's not really a fair comparison because we're also like we're more typed than Python. And if you think about like finance, that's kind of appropriate. So, but people are nervous about kind of going the full jump to something like Java because they've heard about, oh, long compile times maybe or something. So we've kind of managed to sort of straddle the best of both worlds and pull in language features that people found sort of attractive at the time. So there's lambdas, there's a bit of functional programming in there. So. It's a constant debate that we have, and definitely language wars is a very tricky thing. So I think we have gone heavily into the Java space, and so a lot of like web apps or a lot of data processing pipelines tend to be more in Java, and we've built integration between Slang and Java really tightly with kind of like the without going via a web service or something. So that has been a strategy there, and we like Java. I think the tension there is like Slang's been used for all kinds of things, so it's pricing and risk, and that kind of fits nicely in a functional programming language. But then you're like, so there was an effort a little while ago to try Scala for that, but at the time it actually proved too slow compared to this, and I know they're constantly working on that, so that's interesting. Like Haskell is obviously your purest functional language, but because of its sort of delayed execution, it's hard to reason about, and so not many. I mean, there are plenty of finance places that run it in production, but it's kind of interesting. So there's kind of, and then you've got your Python crowd. Like it's used. A lot of the things written in Slang could be just thought of as what we would call data science today. So there's a lot of tabular data manipulation and just kind of stuff that is probably fine to do in Python, and like a Jupyter notebook sort of duplicates some of the stuff we have with we have nice ways to show tables and things, and so there's definitely been interest in that. But I think we worry a little bit about that because Python's still single-threaded, has an interpreter lock. It's not typed that you can use MyPy and some of these things to kind of, so we know like kind of where we are with Slang with 150 million lines of code. It's quite hard for us to kind of break that up and reason about which bits are using which bits at runtime, and we feel like we kind of might have the same problem with Python from a management perspective. So, sorry, that's a long way of saying like all those things are kind of on the table still, but I think that the short answer is we're trying to kind of steer people to specific things for specific use cases, and we'll see how successful. I mean, I would like to see, like Java has done a lot, right? We now have a JShell, there's kind of, they've addressed some of the criticisms with like, you can now ahead of time compile it, so your startup is faster, you can, all of these things that have made people criticize Java, so, and there's some efforts to make, build out data science libraries in Java, so I quite like Java, so I'd like to see some more success in that, but at the moment, I would say our kind of quant community isn't super sold on that part.
I think we're getting told we're out of time.
It's actually two questions. When you say you can't Google it, that would be a big problem for me. And I think many of us do stack overflow-based development. So, but on
Yeah, it's a good question. So the question was, well, you can't Google it, so what do we have, like, and how many people know it, and how do people learn it? It's been used extensively in all the business units, so the knowledge gets parsed down, but also, we have a FAQ system also built in Slang, so there is documentation. There's quite a lot of documentation that's written of varying qualities over the years, but there have been a lot of efforts to pass on knowledge, and we do put that in a search index. I mean, it's not the same as having Google intelligently search for you, and that's definitely way more of a concern, which is why sort of longer term people are interested in, should we even have our own language? And I think that's there. All right, I think we're out of time, but we'll be outside if anyone has any more questions. Thank you.